What's going on, everyone? I hope everyone's well. This will be another episode of the 2017 HSC Physics paper. Today I'll be finishing off the astrophysics section of that paper. Question 33. Okay, Part D, Part 1 asks, use a labelled HR diagram to show the areas in which stars would be plotted for a typical open cluster and a typical globular cluster. So clusters are just groups of stars where they form, basically. Now we can plot these groups of stars on an HR diagram which plots luminosity versus temperature. We've got temperature is increasing, going this way, and we've got luminosity is increasing, going up the scale. It's assumed that this knowledge is here, or that the scales are oriented this way, and we don't have to include any numbers on this scale. It's only a 2-mark question, so we can keep it pretty simple. Okay, so based on that, we just need to draw an open cluster and a globular cluster. Start with a globular cluster because it's easier to orient the open cluster there, for me anyway. You can just do it as you like that. Now, it's a 2-mark question, doesn't have to be perfect, it's going to be pretty simple. It's going to look something like this. Comes to a peak, it's kind of at an angle, and has some stuff going on like that. And then we have our open cluster, which comes down kind of like that. Maybe a little bit further. I don't know. It's around it. Something like that. Now, as long as you draw a diagram that approximates that, you're doing pretty well. You should definitely label your diagram though. In science, we always label our diagrams. So we have our open cluster. We have our globular cluster. And we'll explain what these are in the next section. Cool. So we've answered that question now. That was Part D, Part 1. Part 2 asks, outline the differences between the stars in an open cluster and a globular cluster. This is a 3-mark question. So we describe them, and we're going to talk about them a bit. Open and globular clusters are clusters of stars that form from molecular clouds. Only open clusters contain stars that are in the highest spectral classes O and B. This makes open clusters younger than globular clusters, since the hotter, bigger stars have shorter lifespans. More stars remain on the main sequence line in an HR diagram than globular clusters, where many globular clusters have significant proportions of their stars in the red giant phase. So, the things we note there is that, well, the key information I should say, is that only open clusters contain stars in the O and B class. And if you can't remember what the order of those classes is, you just sing that little rhyme to yourself. O, B, A, fine girl, kiss me. I can't look at these classes without thinking of that little thing, with that little reminder. And we see O and B are at the top of the scale, so we see they're our highest spectral classes. Well, if we look back to our diagram, that's looking pretty good. So, in this section is probably going to be our O and B sort of section. So that little top bit of the open cluster, that's going to be our O and B, somewhere around there. So only they contain the higher spectral classes. This makes open clusters younger than globular clusters, since the hotter, bigger stars have shorter lifespans. More stars remain in the main sequence line in an HR diagram than globular clusters, where many globular clusters have significant proportions of their stars in the red giant phase. Okay, as long as you say stuff like that, where you're doing pretty well, and if you include that key information. Okay, question E. This is a really interesting one. Explain how gravitational forces affect star deaths for a range of solar masses. Now, this is the 6-mark question for the option topic. It's pretty big, and there's a lot of information there. And it's hard to remember all this information. I always remember it in forms of a diagram, which I'll probably draw after I've read my answer for this question. Okay. As stars age and fusion can no longer occur, stars die in different ways. If the original mass is less than 5 solar masses, it will undergo a nova, and if greater than 5 solar masses, a supernova. A nova is just an explosion. A solar explosion, I should say. The higher the mass, the stronger the force of gravity. If the mass is less than 1.4 solar masses, and its gravity is relatively low, then a white dwarf will stabilize from electron degeneracy pressure, so that after this nova happens, the core is less than 1.4 solar masses in this case, and a white dwarf is left behind. It's pretty hot and lasts a long time, and it's being supported by electron degeneracy pressure. It's very, very dense. If the core is greater than 1.4 solar masses, but less than 3, a neutron star will form, which is even denser than that white dwarf, and it's only stabilized by the neutron degeneracy pressure. And then finally, if the mass is even greater than that, then the gravity is even greater than that. And gravity is so strong, it will overcome this neutron degeneracy pressure to form a black hole where everything collapses to a point of infinite density. That should be 2 words there too, by the way. Sorry about that. So, that's the key information there. If you can remember all that, you're doing pretty well. I never remember it when it's like this though. I always refer to this sort of mental diagram I've got, which I'll draw now. So we've got that is the sort of diagram that I sort of picture, and you should have seen in textbooks about how stars form and how they die, from they're born to when they die. So they start off as a molecular cloud, no action happening. They get heavy enough, they start to accrete, and they start to accumulate in the middle, and they have a little protostar going on. They switch up into a main sequence star, burning pretty hot, like our sun is. They start to burn some helium, start to burn some other stuff. We get into a red giant phase. We're going through this phase for a few billion years, burning some stuff, and we start to finally fuse iron. And very soon, after iron starts fusing in the star's lifetime, it explodes. Based on its mass, if it's a small mass, it has a small explosion, it's a nova. And if that core is less than 1.4 solar masses, then we're left with a white dwarf, which is pretty dense. Now, back to the red giant. If it was a big explosion, because the original mass was greater than 5 solar masses, where 1 solar mass is the mass of our sun, by the way, mass of our star. If it's a supernova, there's 2 options. We can be left with a neutron star or a black hole. If that core is less than 3 solar masses, we're left with a neutron star. And if that core is greater than 3 solar masses, we're left with a black hole, where all of the matter collapses into a single point of infinite density known as a singularity. Some interesting stuff can happen there, but that's beyond the scope of this video. So, to answer this question, you need to write something like this, and maybe you could supplement it with a diagram kind of like this. You wouldn't even need to draw the whole thing necessarily, maybe just from the red giant phase, and talk about the different options there. But note, you can't just draw the diagram for this one, because you do have to explain. We do need some words there, I think, for this one. And I think a really key thing to say here is, the higher the mass, the stronger the force of gravity. Because that little sentence explains why these things are differentiated by their solar masses. Because with these different masses, we have different forces of gravity which have different effects. Without these strong gravities, we couldn't overcome these electron degeneracy pressures for the white dwarf, or the neutron degeneracy pressure for the neutron star. Anyway, if you did all that, that would definitely get you 6 marks. Okay guys, I hope that's been helpful. This should finish off. This should be part 2 of question 33, the astrophysics section of the 2017 HSC Physics paper. If you like this video, please give it a thumbs up and share and subscribe. And if you have anything else that you'd like me to do, please leave a comment in the section below. Okay guys, have a great day.